So the next speaker is Nadish de Silva from Oxford University, and he will be talking about K-theory and the topos approach. So go ahead.
Okay, thanks. So I'm going to be talking about some PhD work that's in progress. And the general thrust of the work is to use spectral presheaf as an analog for state space for quantum systems, and use that analogy as part of the noncommutative Gelfand concept, Gelfand duality concept, to try and naturally extend topological constructions to non-commutative C-star algebras in a natural way. So the point is to explore how the spectral presheaf can serve as a notion of spectrum with the non-commutative C-star algebras. So try to study that note idea indirectly without actually trying to build the duality between spectral presheaves and non-commutative C-star algebras, and to sort of explore the relationship between the topos approach and non-commutative operator geometry. And if you don't know what that is, I'll go over it, so don't worry about it. So I think all good talks steer away the ending right at the beginning. So here's the main result we'll be building up towards. Because the beginning of the talk is a bit hand-wavy and philosophical, but then we build towards an actual result. So it's an equivalence between a functor on the operator from operator theory, so C-star algebras, and on this side over here, what we have is a methodical way of building up this functor out of its topological counterpart, so the restricted version, and a presheaf topological spaces, which is quite similar to the spectral presheaf, and then some additional simple processes which I'll explain. And the moral of this, for now, you don't worry if you don't understand anything, any of these labels, anything on here. The moral for now is that we're just building up a non-commutative geometric invariant, so an invariant of non-commutative C-star algebras, by extending methodically the topological invariant. Okay. So first I'll go over some hand-wavy motivation, so you understand why that last equation would be interesting. But a lot of you are probably quite familiar with the beginning part, so I'll sort of gloss over it. The basic idea is that classical physics is a theory that can be expressed geometrically. That is, we have a state space, which is some sort of geometry or shape, which we generally tend to understand in mathematics as being a set of points with some extra structure. The set of extra structure encodes geometric information, for example, what points are near to each other, or maybe a distance function, or smoothness, something like that. And in physics, the points represent the physical pure states of the system. So they specify experimental outcomes for every experiment with certain precision. And then we can model the observables as being real valued functions from the state space, on the state space. Right? So something like energy, the energy function will assign to every pure state the value of the energy that we would get if we measured the system in that state. Okay, so very straightforward classical physics. Time evolution is given by a path through the shape. So it's saying, as time evolves, the state of the system evolves along the path. So your predictions evolve. But basically, the moral is that the physics of the system is completely encoded by the geometry. Okay, once you know at what point you are, and you know where your time evolution is, and your time evolution is often given by geometry too. For example, in symplectic geometry, once you have the Hamiltonian energy function in symplectic form, which is part of the geometry, then that generates the time evolution, the time flows. Okay, so classical physics, the geometry encodes the theory. Now, quantum mechanics cannot admit such a description. That's essentially what the Coke-Spector theorem is saying. You can't describe quantum mechanics as elegant state space, observable picture of geometry. But what if we allow ourselves some more liberty in what we consider to be a geometric space? Okay, then maybe we can accomplish something like that elegant picture. So let me just remind you that historically the idea of what a geometric space has changed quite radically in mathematics. For example, we have the Greeks who considered axioms about lines intersecting and things like that. Descartes introduced n-led geometry, and then Riemann made the idea that you could have intrinsic geometry, curved geometry that you don't try to embed inside a larger space. And then sort of exploded in every direction in the next century with Poincaré bringing in algebraic geometry, Hausdorff talking about topological spaces, so you can actually think of topological spaces being an algebra of open sets which represent nearness, which you can then study without actually thinking about them as being open sets full of points. Hilbert thought about infinite dimensional spaces, and then Grothendieck brought us to like a whole new world where we're starting to move away from the idea of geometry as being a set of points, but rather being a categorical construction. Okay? So here's a vague hand-wavy proposal for what we should consider to be a geometric space. It's just some mathematical object which is studied using geometric tools and intuition, whatever that is. Okay, so I told you it's very hand-wavy, but it could be useful. It's vague enough to maybe start thinking about what sort of geometric space we want to allow ourselves to start thinking about whether quantum mechanics can admit a description like this. Okay. So Galfond duality you're probably all familiar with, but I'll go over quite quickly. Basically, its equivalence here on this hand we have the geometry side of the duality, and over here we have the algebraic side. So here we have compact topological Hausdorff spaces and continuous functions. These are the objects and the morphisms of continuous functions. But you can consider all the values, all the continuous functions to C on the space. You get a continuous complex value, a continuous. You get a commutative unital C-star algebra of functions. Okay. And the great thing is that you can go back by taking its spectrum. So you take all the characters on this algebra, and you get back something isomorphic to the original space you started with. Okay. But physically, this has a very interesting interpretation, which is that moving from the geometry side to the algebra side is like going from the state space to the algebra of observables, of which the actual observable functions are the self-adjoint elements, right, the real value functions. And vice versa, you can go back from a commutative algebra, a commutative unital C-star algebra to spectrum, and that's like going from the algebra of observables to the underlying pure state space. Okay? However, in quantum mechanics, our algebra of observables is not commutative, so this duality doesn't apply. But that does tell us that under this mathematical analog, the geometry of the non-commutative algebra of observables would correspond to the state space, whatever that means, of the quantum system. Okay? So if this is not a non-commutative algebra, its correspondence under some notion of spectrum would represent the state space of that quantum system. Okay, but how can this geometry be described? Okay, we know it can't be something as simple as a set of points. Some X structure, because first of all, under the continuous function functor, that would just give us back commutative algebras. And we also have something like Benno's no-go theorem, which tells us that it's very simple guesses for what the idea of what that geometry could be won't work. But perhaps we can generalize sigma, the Gelfand spectrum functor, in other ways, right? And if you can, it would hold significant interest for foundational physics, for the reason that I was talking about trying to describe what the state space might be. And the topos approach provides a notion of state space, in a way, in the sense that it's some sort of geometric object on which you can model propositions and things like that as subsets, just like classical phase space. So that's a starting point in this work for thinking about how we might try to generalize sigma. Okay? So we're going to try to take the spectral presheaf and try to mold it into something that could be seen as a suitable candidate for generalizing the Gelfand spectrum functor. And I'll talk about what our criterion is for modifying the spectral presheaf or what we're trying to achieve with it. Okay, which gets us to our mathematical motivation. So non-commutative operator geometry is a very active field of mathematical research. And it is actually confusing because you're not actually doing geometry as you're familiar with it. You're actually doing algebra, specifically operator algebras. You're working with algebras of C-star algebras, of one-element algebras, tensor structure, maybe some, just like how in regular geometry you'd have a topological space and you throw on a symplectic form to get a richer structure. You might take an operator algebra and throw in some distinguished operators in that algebra to say, like, represent the metric or something like that. So the essential idea behind non-commutative geometry is that non-commutative C-star algebras can be thought of as an exotic sort of topological space, in the sense that you use Gelfand duality as your guiding analogy. Because in the commutative case, when your non-commutative C-star algebra is actually commutative, then it is actually representing a topological space under Gelfand duality. But we can use the analog you can use the metaphor of Gelfand duality to try to think of a non-commutative C-star algebra A as being the set of continuous functions, complex value functions on a non-commutative space of A. Which is to say, a non-commutative space doesn't actually exist, as far as we know. It's a phantom space. We don't ask, generally, what is the space of which a non-commutative algebra A is a set of functions. We just sort of presume it exists, and that the non-commutative algebra A is a set of functions on it, and then try to work with A as if it were the algebra functions in some space. Okay, so that's the motivating, that's like the central idea, is that a non-commutative algebra A is considered to be C of x for some space x that doesn't exist. But we can use that intuition to guide us. Okay? So how do we do that? How do we actually apply geometric ideas to a non-commutative algebra, C-star algebra A? Well, we use Galfond duality to rewrite all of our geometric concepts from the commutative case in terms of the algebra. So here's a really simple example. There's a topological space and there's an open set U. Consider all the functions which vanish outside of U. Okay? And this set is obviously closed under addition and all that stuff, but it's also closed under multiplication by any other function, continuous function on here, because that will also vanish on U. So that means that it'll form an ideal, all the functions which vanish outside of U. And we can actually go back from closed ideal of the commutative algebra C of x to recover U. And there's actually a one-to-one order reversing correspondence between the open sets of the topological space and the closed ideals of C of x. Right? So we've rewritten a geometric idea, the open set, in terms of some algebraic description using C of x. Okay? Very straightforward, simple example. Here's a less simple example. So this right here is a very poorly drawn Mobius strip. You can see the twist right there. And it's also, this is just to recall, what a vector bundle is. It's not great for what I'm talking about because first of all, I want a vector bundle, not a fiber bundle, so this should be infinite. So it should be like a Mobius strip that's infinitely long with a twist in it. And also I'm going to be considering with complex vector bundles. And this is a real vector bundle, but just the idea, hopefully, does everybody know what a vector bundle is? Yeah, okay, good. So we want to generalize the idea of vector bundle from geometry to non-commutative geometry, right? So we want to encode what a vector bundle is in terms of the algebra functions, C of x, okay? So how do we do that? So notice that if we have a vector bundle, E over x, then the set of all global sections, gamma v, forms a module over C of x, right? We can multiply global sections by a function of the space. Pointwise, basically, you just stretch every vector by the value of the function of that space, okay? Pretty straightforward. And the question we might ask is, can we characterize which C of x modules arise this way? And yeah, you can. So here's a hint. The module is always going to be finally generated because our vector spaces are finally generated. You use some compact arguments to extend it. And so the module associated with the global sections vector bundle is finally generated. And then there's a theorem from geometry which says that if we have a vector bundle over space, there exists another vector bundle, so that if you direct sum them together, the direct sum you take fiberwise, you get a trivial bundle, right? So that just tells us that if you translate that into the algebra, that says that the module of global sections is going to be a projective module. It's a direct sum end of a free module, okay? And then you have the Serre-Swann theorem, which says that this fully characterizes which modules come from vector bundles. So there's a bijective correspondence between vector bundles over space and finally generated projective C of x modules. Okay? So we've now characterized the notion of vector bundles for C-star algebras, non-commutative C-star algebras. Basically because, yeah. And you can keep going with this dictionary, with this concept, and just start anything you think of. For the most part, you can think of a topological concept and translate it into algebra in terms of C of x, right? So a continuous C-valued function in a topology is just an element of the algebra, right? It's an element of C of x. A real valued function is just a self-adjoint element of the algebra. We already saw how open sets and vector bundles translate to closed ideals and finitely projective modules and so on. But you can go on to things like measure theory and like topological constructions, like compactifications. You can go much, much further, incorporating all manner of like topological, measure theoretic, and differential geometric tools. The whole program of, Cons is talking about reconstructing spin manifolds and things like that. So you can put a lot of structure on your C-star algebra in terms of and the miracle, I think, of non-commutative geometry is that we can use these algebraic descriptions of these tools to study non-commutative algebras simply by replacing in our dictionary every instance of C of x, which comes from a commutative C-star algebra or from the topological case, with just A, which represents a non-commutative algebra. If you just do this simple translation, switch out C of x with A whenever we have our algebraic description, and then we can study a non-commutative algebra using geometric tools and geometric intuition. For example, if I want to describe what a non-commutative vector bundle is, what a vector bundle is over a non-commutative algebra A, we used to have the description finite projective CFX module, but now we just replace CFX with A. Do you get a question?
But, I mean, sometimes commutative algebra theories, the concepts diverge when you go non-commutative. So instead of ideals, you've got left, right, or two-sided ideals.
Yeah.
And instead of modules, you have to choose, I suppose this is going to be symmetric, you have to choose left or right modules.
Yeah, well, in C-star algebras, yeah, I think modules are
Yeah,
bimodules.
because it's got the involution.
Yeah.
But the ideals, you have to choose whether it's one-sided or two-sided, don't you?
Closed ideals are always two-sided, aren't they?
I don't know, but I mean, there are choices to be. It's not a straightforward translation.
Okay. Well, sometimes it's not a straightforward translation. Sometimes you have to use. You pick what works, what generalizes properly, like what's actually going to work in your when you're writing a definition for some. Sometimes like for example, tensor product, like which tensor product you can use. You sort of have to, I think, try different ones, and then you fill in a dictionary using. Because you get extended to the non-commutative case, and some generalizations will work and some won't. Okay, so what we have is a very powerful kit of geometry-inspired tools which work on non-commutative algebras, despite there being no actual underlying space as far as we know. And I think it's quite remarkable. I mean, you just drop commutativity, and you can't just drop associativity and study non-associative system algebras. There's something special going on in the transition from commutative to non-commutative. So that brings us to our first bit of mathematical motivation, which is this method seems unreasonably effective, that we can use geometric intuition to study non-commutative operator algebras, and that it cries out for some sort of justification in the form of an explicit geometric correspondence between some kind of geometric object and non-commutative algebras, i.e. some sort of generalization of sigma, the Gauss vector functor, right? It seems like there should be some sort of underlying geometry. And the second bit of motivation has to do with the approach of non-commutative geometry, which is to use this dictionary, which is very cool and effective, but it seems quite cumbersome and opaque. It sort of tends to obscure the geometric flavor of the tools that we're using on non-commutative algebras, right? So I think it would be quite nice if we had a very direct method of going from geometric to non-commutative algebraic tools that goes through some explicit geometric picture of what a non-commutative algebra should be, and that would suggest that if we had an explicit picture of what a generalization of sigma should be, that should suggest such a method. Okay, so the motivation, one of the guiding ideas behind the work is to use natural extendability of geometric tools as a criterion for thinking about how we should generalize, how we should extend sigma. Right, that's the guiding principle. Is that if we want to generalize sigma in a way such that it leads to a natural method for extending geometric tools. So I'm going to go over K-theory quite quickly, just enough so that you know what you need to know, but it's actually a very deep, technical, rich topic. Because K-theory is a topological cohomology theory, which is one of the oldest. It's the first generalized cohomology theory discovered. Has been very fruitful in topology, but then extended to non-commutative algebras. And is again very, very fruitful there too. And that's the key invariant that I was thinking about in my work, that I wanted to naturally extend from topology to non-commutative system algebras. So, yeah, the extension of this topological homology theory to homology theory for system algebras is one of the best examples of one of the biggest successes in non-commutative geometry. So, topological K-theory is an invariant of topological spaces, which is based on different sorts of vector bundles you can place over a certain space, right? So it characterizes, it sort of just gives you some, reduces a topological space to some more simpler information about it. That simpler information is the different classes of vector bundles you can put on it. Because if you deform a space continuously, that's going to keep all the isomorphs in the classes of vector bundles the same too. Whereas the latter version, the version of K-theory for non-commutative C-star algebras, it's defined using this dictionary that I described earlier, and it's a very powerful invariant. In fact, there's a whole program of classification of C-star algebras by K-theory that's underway. And in many cases, you can actually recover a C-star algebra from its K-theoretic data. So my master supervisor, George Elliott, who I worked with back in Toronto before coming to Oxford, who's very active in this field. That's how I got to be thinking about this in the first place, because I had some experience with K-theory before. So the way you build up topological K-theory is quite simple. So, for a cohomology theory, you want a chain of groups, but you can actually you actually generate all the groups from just one single group, which you get from the K functor. So you define this one K functor, and then you get the whole series of groups in a straightforward way. And so there's one topological K functor, and you get your Abelian group from topological space. And you build it up in a very simple way. So you have a space X, and you just consider all the isomorphism classes of vector bundles, that should be complex vector bundles, over X, right? And then you can add them with direct sum, with a Whitley sum, which is a fiber-wise direct sum, right? And then even all the isomorphism classes, that's still a semigroup. And it's also abelian. Okay? So you can form this semigroup of complex vector bundles under direct sum, up to isomorphism. And then all you have to do is just take the Grothendieck group of that, which is just the simplest abelian group you can get from an abelian semigroup. It's like similar in the way you get Z, the integers from the natural numbers, just throw in formal inverses. So you have pairs, this represents A minus B and C minus D, and then you have this equivalence relation, which is like moving the D over to one side and the B over to one side, so you just have addition. There's a little mistake in here. There should be, there exists E such that you can add E to both sides, but that's less important. The point is that you just take the simplest abelian group that you get from it. Right, so very simple, that's K-theory, right? Vector bundles, semigroup, abelian group, that's it. You form higher groups by composing with this operation on topological spaces, where you just basically form finite cylinder, pinch the edges. That's a suspension. So K0 of group is just a K functor. K1 is just K after you take the suspension. K2 is after you take the suspension twice. It doesn't matter, but I don't believe it's really important. The important point is that once you have the K functor, you have the whole thing, the whole series. Okay. So how do we define K sub 0, which is the K0, which is the operator K theory, which is a functor from unital C-star algebras to abelian groups, i.e. operator K theory? Quite easy now. We just replace a vector bundle with finite projective A module. Just use a dictionary, right? So we form this semigroup whose elements are isomorphism classes, so finite projective A modules with direct sum. And then we take the Grothendieck group, and that's it. That's operator K0. Okay? So hopefully it's not too hard to see that if you restrict K0 to the commutative case, that should be commutative system algebras, then you just get back K theory up to translation by the Gelfand spectrum functor, right? So if you think of the commutative case and the topological case as being exactly the same because they are under the Gelfand spectrum functor, then this equation here expresses how operator K0 extends topological K theory, which is that if you restrict it to the commutative case, it just is the topological case with this thing here doing the translating. Okay. Now the definition of K0 that I presented is not very useful to work with practically. It's just like saying consider all the modules. It's not easy to work with. So you have to sort of do some work to express it in a way that's actually lends itself to computations and proving theorems. So the way you do that is you take a C-star algebra A, you consider all the matrix algebras with elements in A, and then you take the limit of all of them, so an infinite dimensional matrix which contains all the finite ones. You consider projections in this matrix algebra with orthogonal direct sum, and then you quotient out by what's called Morley-van Neumann equivalence, which is this maybe a little bit of obscure equivalence relation right here. It's basically like saying projections which are the same size and related. And then you take the Grothendieck group of that. Okay. So can you still tell how this definition is geometrically motivated? That's my question. I mean, is that still preserved in this process of going from a topological invariant to this guy right here? I mean, you you can see where the algebra comes in because the matrix. So if, the reason where this all comes in is that okay. So what's a finite free module over A? Right. It's going to be a to the n. Right. And how do we describe projective modules? Well, it's a splitting of a free module into two subspaces. Right. So we can identify the module with the subspace. So that's where the projection comes in. The projection is identified with the subspace in the direct sum splitting. So that's why we're taking projections in all the matrix algebras, because that's like splitting a free module into two direct sums. And this quotient is like identifying subspaces that should be equivalent because they correspond to isomorphic vector bundles. Okay. So that's where the geometry is. So it's quite obscure, I think. So now we'll finally have gotten to the main problem, which is we have this equation k0 when restricted to the commutative case is topological K-theory. But can we generalize it? Can we generalize sigma, this translation from topology from algebra to geometry? Can we generalize it so that it holds in the general case? This is a very vague hand-wave equation. This is a conceptual equation. So can we generalize sigma to sigma prime so that we can drop this restricted commutativity and associate to non-commutative C-star algebra its extended spectrum, some geometric structure. It's a geometric structure, so it has topological data, K-theory data, so that we can extract from that the operator K-theory data of the original non-commutative algebra. Okay, and in a way such that this extended sigma prime when restricted to the commutative case should essentially be the Gelfand spectrum functor. Right. So that's the main problem that I'm after is getting this functor right so that this equation in a sense holds. So our starting point for how we should generalize sigma to sigma prime comes from the spectral presheaf for the reasons I talked about earlier in the talk, which is that it represents something like a state space. And the great thing about it is that it actually admits a very natural way of extending topological functors, which have a co-complete codomain category, to functors on non-commutative C-star algebras, such that the non-commutative version extends the original topological functor. Okay? There's a way of taking a topological functor, using a structure like the spectral presheaf to give you a new functor on all non-commutative algebras, such that when you restrict the commutative case, you get back the original functor. Okay? And the idea is quite simple. Spectral presheaf is a presheaf of topological spaces, so we can just apply the topological functor to the entire diagram to get back a presheaf of, say, abelian groups in our case, and then we just take the Colimit of the entire diagram to get one single group, and then we can then compare that to. So if we start with a topological K-theory, we can just compare that to operator K-theory and see what we get and see if they match up. So that's the first thing I tried. I tried it with spectral presheaf. Oh, and you should note that when the algebra is commutative, then in the spectral presheaf, that commutative algebra is also terminal in the spectral presheaf diagram. So when you took the Colimit, you just get back the functor valued on that thing. So it's obviously an extension. So we don't have to worry about the commutative case. It's going to extend the functor. Well, what about the simplest non-commutative algebras, which are the matrix algebras that we see? Well, operator K-theory says that its K-theory group is the integer Z, but if you apply the construction I talked about earlier with the spectral presheaf, you get an infinite direct sum of copies of Z, because you have a whole bunch of commutative diagonal algebras that differ up to unitary. There's no terminal element, so there's no relations between them. So that's not good. Spectral presheaf doesn't work on the simplest non-commutative algebras. But there's a simple fix. We just throw in more morphisms, and that'll identify more elements in the diagram and simplify the Colimit. So what I tried throwing in is morphisms that come from unitaries. So an inner automorphism of a unital C-star algebra is one that's given by conjugation by a unitary. Okay? So it's a morphism that sends A to U inverse. Now you can restrict that to an abelian subalgebra, and that's going to be a morphism between abelian subalgebras. Right? So we're going to throw in all the morphisms which arise in this way, where phi is phi is an inner automorphism, so it's given by conjugation by unitary. And we restrict it to Abelian subalgebra, where where this whole phi of u is contained in V. So it's like a horizontal connecting algebras of the same size plus inclusions. And then that's going to be our definition of this sigma sub un. Un stands for unitary. It's going to associate to a noncommutative algebra the same, so it's going to associate a diagram which has the same objects, the Abelian subalgebras. The morphisms are from the same as spectral presheaf but enriched, inclusions plus also these restrictions of inner automorphisms, unitaries. And then ask, okay, well, what happens if we take the diagram that this suggests of the matrix algebras, apply K theory to the whole diagram, and then take the limit? Well, we get back Z. That's good. Okay. And of course, it's this idea of this diagram still works in the commutative case in the sense of giving an extension of K or of any topological functor, because the automorphisms of commutative algebra are just inclusions, because conjugation by anything is identity, right? So that's good. So we have this extension of the K functor which agrees with topological K theory in the commutative case, and in the simplest, in the finite dimensional non-commutative case. So far, so good. Okay? Right, so the question is, will this, which I call K tilde, the extension of K theory, work on all unital C-star algebras, not just the finite dimensional non-commutative ones and the commutative ones? So I'm going to get to that question in a second, but first I glossed over a lot of technical details so far, and I want to just lay them all out so it becomes clear exactly what I'm asking and that you're convinced this has a technical grounding. So what I want to do is lay down the technical, it's very straightforward actually, the technical machinery that I needed to be able to ask this question. Because I was sort of throwing in some vague things about like take a diagram and then take the K theory of the whole diagram and then take the Colimit of it, and then there's some issues that need to be addressed. So the most important thing is that spectral presheaf and also this sigma sub un, which I made up to make this K theory stuff work, are presheaves whose base category comes from whose objects are the subalgebras, right? So that base category is going to vary as your algebra varies. And but I'm going to be taking colimits over these diagrams, and that means I have to take colimits between morphisms of these diagrams. And generally, colimits are generally defined on fixed base category, fixed functor categories. Whereas I need to be able to take, I have algebras A and B. They can have different diagrams, but also a morphism between diagrams of different shapes. And I need to take the colimit of both and also ask what's the colimit of the morphism between them. And that's not going to work in a single fixed base category, functor category. So we need to generalize the colimit to accommodate morphisms between diagrams of different shapes. Okay, that's what we need. Simple solution. I'm just going to define this category, which I call the category of all diagrams in C, to be the category of diagrams of every shape, right? So all functors from J to C for any small category J, right? So it's sort of like a disjoint union of all the functor categories for all small base categories. Okay? And the morphisms are going to be pairs of a functor and a natural transformation. So here's our first element of the category. Here's the second. So one goes from J to C, one goes from J prime to C. So the morphisms are going to be given by a pair F and eta, where F is a functor from J to J prime, and eta is going to be a natural transformation from this guy to this composition. Okay? And you can sort of figure out how they compose quite naturally. Stick some diagrams onto each other. But the idea is that, like, yeah, this is a diagram of shape J. Here's a diagram of shape J prime. Right? This is going to relate the shapes, and then you have a natural transformation which relates the diagrams. So this category is great because it allows us to accommodate the spectral presheaf as well as a whole bunch of related structures like the sigma sub un I was talking about earlier. So the spectral presheaf can be thought of as a functor from unital sister algebras or whatever, to diagrams of topological spaces, right? So it has to associate to every algebra a functor from something to top, right? And the something is the inclusion functor. The inclusion functor from the subcategory of top, whose objects are the abelian subalgebras and whose morphisms are the inclusions, plus, and then you take the spectrum of the whole thing, right? So instead of associating, so the spectral presheaf is now represented as a subcategory of top, and it's represented by that inclusion functor into top. So that's how we can think of the spectral presheaf as a diagram of topological spaces. It's an inclusion functor from the subcategory to top. Same with sigma un, which is what I described earlier, which is the spectral presheaf plus inner automorphisms, right? It's just sigma sub un associates to an algebra A the subcategory of top, whose objects are the same as the spectral presheaf, and whose morphisms are also the inclusions and the inner automorphism and the take the spectrum of the whole thing. So that's also a diagram of topological spaces. Okay, so that's some geometric objects I'm going to be thinking about as possible generalizations of sigma. So we go from a single topological space to a diagram of topological spaces. And note also that if you have any functor from C to D, this is going to naturally induce a functor from diagrams of C to diagrams of D, which I'll also call by the same name because it's so simple. You just apply that functor to the whole thing to get another diagram, apply it to every object, apply it to every morphism. Okay? So, the remarkable thing about this construction, which I found, which works great for my purposes, is that there exists a generalized Colimit functor from the category of diagrams in C to C, when C is co-complete, which sticks together all the Colimit functors from all the fixed base category functor categories all in one, but also has some more important action that we need, right? So on objects, what this Colimit functor does is just assigns it the standard Colimit, which is as if it was taken in the functor category. Okay? So you just pretend that your functor was in its natural functor category and take the Colimit to get the objects. Okay, so it generalizes all the Colimit functors on objects simultaneously. So the morphisms, remember, they're pairs of a functor and a natural transformation. So if your first functor is an identity, so that you're taking a Colimit between diagrams of the same shape, and your first thing is the identity, then it's just going to associate to this natural transformation exactly what you would expect from the functor category. Okay? So in that sense, it also generalizes the morphism action of all the Colimit functors from all the functor categories. But what we need, and what this gives us, is the ability to take the colimits for diagrams of different shapes. So if I have a diagram over J and a diagram over J prime, and I have a morphism of the kind that I specified between functors from J to C and J prime to C, functor and natural transformation, this is also going to assign a morphism between those colimits, which is compatible with all these conditions that I suggested earlier. Okay, so it actually is an extension of the Colimit functor because it does everything the other Colimit functors did, but it also gives us extra ways of assigning morphisms to diagrams of different shapes.
So
okay.
was that a known construction in category theory?
This?
Yeah.
I don't think so.
Yeah,
Do you know
surely.
con extensions?
I've heard of them. It could. I know it's like a simple thing.
Yeah.
I just have not seen it explicitly written anywhere.
Look at
I didn't find it in a book.
Chapter 10.
Pardon?
Chapter 10 of McLean.
Yeah, this is a con extension.
Well, I don't know if it is. It's,
I'm not sure. We looked around with it.
I mean, it seems so natural and straightforward that I assume it's somewhere in the category theory literature. I'm not that familiar with the category theory literature. I just came up with this for these purposes, but I'm sure it's quite, category theory literature goes quite deep, and I'm sure it's in there somewhere.
Yeah, I'm trying to think where's a good reference, but yes, this is no.
I mean, I suspect that this is some sort of, one category. If you take some two category and then restrict to the one category.
What's the composition of morphisms?
It's given right here, so that you compose the functors, and then you compose the natural transformations.
Horizontal composition, natural transformations. This is the category I call co-presheafs over C, basically. Actually, this little triangle is the best way to visualize it.
Well, anyways, the point is that this gives us the technical machinery we need to interpret this equation, right? So sigma prime is going to take an algebra to a diagram of topological spaces, right? Then our topological functor f is going to take that from a diagram of topological spaces to a diagram of C, where C is the original topological functor, and then we can just take the whole Colimit of the whole thing, right? So this here, this takes in topological functor f, and then spits out a functor on noncommutative algebras without anything else. Right? The only input is f, and then this process just does the rest. You can actually give rather simple conditions on a functor sigma prime to ensure that this equation, when you restrict it to the commutative case, actually just gives you back the original topological functor. And the simple conditions basically have to do with, in the commutative case, the algebra should be terminal in the diagram that you associate with it. So now to sum up where we were before I took this little technical interlude, now that we have this language, so this here is called this would be called the sigma prime extension of f, because you can swap out the sigma prime with other associated ways of constructing diagrams from space. So where we were before I talked about this diagram stuff was that the sigma sub un extension of topological K-theory, right, it agrees with K0 in the commutative case, of course, because it's an extension, but also in the finite dimensional non-commutative case, that is matrix algebras and their direct sums. I didn't talk about why direct sums work, but it's pretty not that hard. Okay, so how about generally? Will this equation hold if I put in sigma un and k here, hold for all C-star algebras? That's the question, right? That's what that would say. The answer is close. Close. Not quite, but close. And this is the actual theorem. So you'll notice that there are two modifications from this conjecture to this theorem, okay? The first is that we've precomposed with this curly k thing. Sorry about throwing in another k, but that's just standardization. You can blame the Germans for that one, because k is German for a class, and this k is German for a compact.
If you did them both in English, it would be C.
Yeah, but it's clearly the German.
That would be C theory.
Okay, so yeah, I'll talk about what this is, and you'll notice I've changed sigma sub un to this sigma sub f, and these two are actually quite closely related, very closely related. I'll talk about that. So this is barely, a very, very, very close equation to what we were hoping for, and it's interesting to think about why we have to modify it this way, what this means, what's the relationship between this functor. Well, this doesn't actually. So this functor and this functor. Okay, so I'll explain what these modifications are. Okay, so here was the hope, and here's the reality. So this k functor here is called the stabilization functor, and it's a functor from C-star algebras to itself, and it's a functor under which operator K theory is known to be invariant. So stabilization is actually a very important construction in operator K theory, because all algebras, if you take a stabilization and then take the operator K theory, you don't actually change the K theory. I mean, the very first thing you do when you take operator K theory of an algebra is you just take a stabilization at the first step. So it's not really that surprising that it shows up. And yeah, so I'll talk about what it is, but it's important to note that K0, it doesn't change when you throw in this stabilization in front of it. So if instead of trying to reconstruct K0, we talk about reconstructing K0 precomposed with stabilization, then this equation seems interesting, right? Because now this K0 part of this equation corresponds to the sigma f extension. Okay? And sigma f is closely related to sigma sub un. So I'll talk about first what stabilization is. Stabilization is basically tensoring with the compact operators. Compact operators are the finite rank operators on the separable Hilbert space. So basically what you're doing is you're taking, you can show that this is basically like taking all the matrix algebras in A.
Isn't the closure?
It's a
Mhm.
more
And sigma f, I promised it was very closely related to sigma sub un, and it is, because you take the same morphisms, which are restrictions of inner automorphisms, but instead of taking all the commutative subalgebras, you take just the finite dimensional ones. an algebra, I would have called it A, but actually by the time it gets to sigma sub UF, we've already done K to it, so it would be A tensor K, so I didn't call it A to not confuse you. So we'll call it for a B. When you give sigma F a B, it takes it to a diagram of topological spaces, which you get from, well, first you take it to commutative C-star algebras by taking the finite dimensional commutative subalgebras of B. And the diagram, you take the inner automorphisms, apply sigma to the whole thing, and then you get a diagram of topological spaces. Okay, so, and that's it. And then you can prove that this works. Okay? And a quick proof sketch. It would take too long to do the whole proof. But you basically express the K0 group as being projections in A tensor K. Before I defined it as being projections in all the matrix algebras, but it's essentially the same thing. So it's projections in A tensor K up to unitary equivalence, which says that two projections are equivalent if they differ by conjugation by unitary in the unitalization of A tensor K. The finite dimensional Gaussian subalgebras, they're always isomorphic to C to the n, so they pick out the projections in A tensor K. And then on a choice of morphisms, conjugation by unitaries, identify equivalent projections in the colimit. So it's sort of a straightforward idea, just a lot of technical junk you have to go through and start coming up with categorical constructions to even have it make sense. But then at the end of the day, it's not a terribly complicated idea. Or I guess it's not terribly complicated if you study it for 2 years. So I'll talk about some questions I want to think about in the future maybe, or if anyone else wants to think about it, please do. One natural question I think is that, well, I gave natural methods for extending topological functors to functors on noncommutative C-star algebras. So we can ask, if our topological functor had, with a cohomology theory, what sort of homological properties are preserved through this extension? I mean, when I say this extension, there are lots of extensions. You can come with an extension for every possible way of coming with a diagram. You can. So it's interesting to think about what sort of homological properties are preserved by this, by these extension processes. And you might expect some to be preserved because, like, what are the components of your extension, right? You have like this diagram, this thing of associating diagrams. Okay, so that's interesting. This we're assuming to be a cohomology theory, so it's going to have all sorts of homological properties. This is the colimit, right? The sigma is like supposed to be an equivalence of categories. So most of the components of these things are things you expect to preserve those sort of properties. So there's a reason to think why there might be some homological properties that are preserved by extending cohomological theories. Other questions have to do with the discrepancy between the conjecture about extending K theory and then the actual reality of the theorem, which is how does our definition of K0 compare with the simpler sigma sub UN extensions, right? Is it possible that maybe the sigma UN extension of K theory actually is still a homology theory? It's just not a stable homology theory. It's just not one that is invariant at a taking stabilization, right? It could still be an interesting geometric invariant that's just not been known, or maybe it's not close. I don't know. So another question is maybe we can repeat this procedure with other non-commutative geometric invariants, because there's a whole dictionary full of correspondences between cohomology theories of topology and homology theories of C-star algebra. For example, dynamical homology and cyclic homology. But this would require modifying all sorts of things about this proof, because we were talking about different kinds of algebras, and maybe we need a different kind of diagram. I haven't really looked at this yet. But maybe, yeah, but what about the general idea of extending topological ideas through presheaves of topological space associated with them in a natural way? How might that work? Because that will sort of maybe, I think, get us closer towards understanding what sigma should be using this natural extendability criteria, which I think is a natural one for thinking about the spectra. Or you could even try this with other examples of commutative dualities, besides Gale-Fine duality. Or anytime you can take a non-commutative algebra, break it up into a diagram of commutative algebras, apply invariants to commutative algebras, and then compare the colimit with a non-commutative version of that invariant. Yeah, that's it. Thanks.
Yeah.
You already included it maybe in the further questions part, but is there a reason why you see K0 all the time, but have you looked at K1?
Well, the thing is, once you have K0, then you have the rest of, once you have the K0 functor, you have the rest of the functors, because you're just composing with suspension, or at least the noncommutative suspension. So it's like in the topological case, you'll need the topological K theory, and then you can generate the other groups by composing with suspension.
In your main results, so which have on the left hand K0 is Colimit, etc. So we have it because it's 2 slides ago. Yeah. So does that express the fact that the conventional K theory for C-star algebras can be given in that way, or is the theorem that you have a well-defined functor which may be different from K0?
No. It's saying that operator K0 is this.
Okay, so that's almost unbelievable. So that's is only sensitive to the commutative subalgebras.
No,
Depending how much this tensor of the complex operators matters.
Yeah, because this is like taking all the matrix algebras in A,
Yeah.
and then the abelian subalgebras are isomorphic to C to the n, right? So they're like taking a bunch of orthogonal projections, right? So they're projections in matrix algebras, and then the diagram has the inner automorphism, so it's connecting unitarily equivalent projections. So this is just a rewriting of
I see.
the definition of K0.
Certainly gives a new picture.
Yeah.
The power is in the shape of the diagram. So it's really about the structure of the complex theory, and in this case the 4-dimensional subalgebras. Yes, that is one that I found the same. So it's really how things are glued together in the diagram. Because locally, of course, it's totally trivial topological groups.
So thank you, I mean this is very nice. Two remarks. Chris Heune has already looking at CA together with the inclusions. So he has quite a bit of theory on this. So you may want to look at this.
CA?
The commutative subalgebras together with all the inclusions. So he has looked at this category and the corresponding spectrum. And the other one is that the Sarah Swan theorem that you mentioned. It's one of the highlights of where topos theory can be applied to C-star algebra.
Oh yeah.
So the work by Banaszewski and Mulvey. I don't know whether you're aware of this, but this may help you to simplify something. Not
Okay.
sure. I can provide you with reference.
Yeah, sure.
Yeah, thank you very much.
Another way which is sort of orthogonal to maybe your talk, but since we're obsessed by the C of A or the U of H poset of all commutative subalgebras, with the Alexandrov topology, that has a topological K theory, K0. So how is that related to the K0 of A? So this question is independent of your results. It's a question about ordinary K theory compared to some topology. Have you thought about that?
Nope. No, I'm not sure.
No, I'm not sure.
Does K theory work for non-algebra spaces?
Interesting point, but it's still somewhere, isn't it?
No.
CA is not even somewhere.
Well, you can take its ideal conclusion and filters with Scott topology, then you make it forcibly so.
Certainly the definitions are okay, but maybe it doesn't have the usual properties for non-algebra spaces.
Sounds like there's enough to discuss during the drink session, so let's thank Nadish again.